Well, hello, fellow electronics enthusiasts. Today we're going to talk about the voltage regulator, variable voltage regulator, LM317 or LM317, whatever you prefer. And the easiest way to understand what it does is just to get, you go on Google and you just get the data sheet. So LM317 datasheet PDF, and it should be from Texas Instruments. Okay, and those are very useful. I mean, it's a bit, it can be tedious to read because they describe a lot of stuff, but they give you like typical usage for it. So they give you examples of circuits. Okay, so first, no, you don't want that. Okay, so this gives you the pin configuration depending on the package, depending on the way it's packaged. But what's important is all those specs. Okay, so let's here. So the output voltage, it can vary from 1.25 volts to a maximum of 37 volts. The differential between the two input-output voltage has to be at least 3 volts. So has to be minimum 3 volts. But you don't want it to be too large, otherwise you're going to have too much power to dissipate across the input and output pins. So the regulator may emit a lot of heat, so that you have to dissipate with the heatsink. Okay, so let's keep going. Output current. Okay, this is important. So minimum 0.0101 amp, meaning 10 milliamps, and max is 1.5 amps. What else is interesting here? Not too much. Let's keep going. We don't really need this. Okay, so this is what's inside. Okay, typical application, that's what you want to look at. Okay, so you have your input. So basically, if you want to do like a power supply, a regulated power supply, so the input would be after you do the transformer, after the bridge, the full bridge rectifier, and you're probably gonna have a filter capacitor, a big one, before you put the voltage regulator. So on the VI as input, there would be like a big filter capacitor around here. So here they are just showing the circuit with the voltage regulator, but think that there is like a transformer, full bridge rectifier, and the filter capacitor around here. Okay, so basically how it works is that R1 is fixed at 240 ohms, and you have the voltage across R1 fixed at 1.25 volts. And the R2, which is variable, determines your output voltage. And the output voltage is can be between 1.25 to 37 volts, I believe. So that's about it. So here they explain, so R1 and R2, so R1 and R2, but mostly R2 are required to set the output voltage. Okay, so edge is for adjust. because this is where you adjust the output voltage. That's the pin that where you can that's the pin where you can adjust the voltage. So here it's recommended to have put a capacitor here, C edge for adjustable. So it improves the ripple rejection. Okay, let me try to explain that ripple rejection thing. So when you do like a power supply, so the signal, so this is your AC signal, like a 60 Hertz mains signal. When you go through one diode, it looks like this. You lose half the signal, so you end up like this. And if you put a full bridge rectifier, you are like this. Okay, so now, and then this is the ground, and then you put like a capacitor here. I should have put it like this really. You put your big capacitor here, then it's gonna look like this. So what happens is that, let me do it a little bit better. Here, what's gonna happen is that the capacitor is gonna start discharging, and then you get the impulse back. So it's gonna look like this. Okay, so here it starts discharging, and then you get the impulse back. Discharging, impulse. So it looks like this. And that's the ripple. So I mean, of course it could be better, but let's assume that your DC looks like this with the ripple. So maybe let's say it's like 2 volts. Now when you increase it, when you play with your potentiometer on the adjustable pin of your voltage regulator, that ripple might get higher. Okay, let me get rid of this. If you go higher, let's say at 5, that ripple is going to be more. It's going to be more of an effect. So the ripple rejection prevents that. So the ripple is going to be the same. So the ripple will not get worse, basically. It's going to stay the same. So that's ripple rejection. So that's why you have that C edge in the circuit. Okay. So it prevents amplification of the ripple as the output voltage is adjusted higher. It's exactly that. And you have a D2. So this is a diode, protection diode. There are 2 protection diodes. There's a D1 here and a D2 there. So let's look at the D1. Basically, D1 is a protection diode to protect the regulator. You don't want current to go this way towards the output and go inside there. You don't want that. So that's why you have a diode here. That way the current doesn't go this way, it's gonna go that way, because the diode has a very low impedance, so current chooses the path of least resistance. So instead of going this way, it's gonna go that way. So that's one protection diode, and it's mostly because of this guy, the C0. That capacitor, when it discharges, it can put out a lot of current here, and this current can go towards the regulator. So in order not to have that, you have a discharge path. It goes this way, and it doesn't go inside the regulator. So the other protection diode is this one, the D2, but it's the same principle. You have a C edge. That capacitor, if it discharges, it's going to go through the path of least resistance. That is this one, or low impedance, the path of least impedance, I should say. So it's going to go this way, and then it's going to go here through the second protection diode. So you have one protection diode here because of this guy, and one protection diode here because of that guy. And it's actually explained here. So here C1 or Ci is recommended. But in our case, since we probably already have a filter capacitor here, you probably don't need it, but it doesn't hurt, I guess. It's just to get rid of noise, basically. It's like it's a bypass capacitor, or decoupling, sometimes it's called. Okay, C0, so that capacitor here, again, is just to get rid of noise. So it's improving the transient response, but is not needed for stability. So that's why you have C0 here. So protection diode, I just explained. D2 if C edge is used, and D1, and you have D1 if C0 is used. Okay, so that explains it. And here it shows what V output is supposed to be. So that's the formula. V output equals Vref. Vref is the voltage across R1 times 1 plus R2 over R1 plus I edge, which is the current that comes out of the adjust pin, times R2. And this one is negligible because I edge is about 50 to 100 microamps. So it doesn't, you don't need to worry about that one. Okay, so here I have reproduced the circuit. So you have your voltage regulator here, you have the edge pin with I edge coming through here, but I edge is negligible. It's negligible. You have your R1, which is at 240 ohms. You have the voltage across R1, which is called Vref, and it's 1.25 volts. And you have your variable R2, which is the resistance you use to control the output voltage. So the formula, it's very simple to get if you assume that the I edge is negligible, because it's just if I edge is negligible, you can just get rid of this part here. So now you just have a voltage divider. So you have VO or V output at the top, and you have ground here. So you know that using the voltage divider formula, VR1, which is Vref, equal R1 divided by the sum R1 plus R2 times VO. So now, to get VO, you multiply by R1 plus R2 and you divide by R1. So you get R1 plus R2 divided by R1 times VR1, which is Vref. And this is actually, this is R1, this is 1 plus R2 over R1 times Vref. So that's your output voltage, the formula. If you assume that I edge is about 0. In reality, it's like 50 microamps or 100 microamps. So that's the formula that's given in the datasheet. So I think I'm gonna stop here. If you like this kind of video, I can make more. Please like, comment, subscribe, as it helps my channel. So see you. Bye.